Okay, recording is on. So Math8680, Spring 2021, topics in combinatorics. And Sam, what are you saying? Yeah, participants are not defaulted muted when they enter, but that's okay. I'm thinking we can manage it. If it gets to be difficult, then we'll do something else. We'll change the default. That brings up a good point, which is, please, most of the time just stay muted and then unmute yourself when you want to say something. And please do speak up. We like to have questions in class. So before I talk about any of the content of the course, since this really is a course at Minnesota, let me point out the particulars here that I've already written ahead of time. Notes and videos are going to be posted on my syllabus page, which you probably found. There are some registered students, and the course requirement, which is kind of loose, I'm going to be pretty flexible, but I decided to make it two possibilities. Either do 8 homework problems, and I'm saying 4 from each half. When I say half, basically the course is going to fall into sort of 2 parts. The first part is going to be very polytopal. It's going to be focused on face numbers of polytopes, simplicial polytopes, rings that come up there. And there's a whole bunch of questions that will get expanded, but it's on my syllabus. You can find this list of questions that have to do with the first half of the course that will help deepen your understanding of some of the material, Stanley-Reisner rings and things like that. And you should do 4 from there if you're going to do homework. And then that list suddenly starts saying, okay, these are starting to be some questions from the second half. That will get expanded. That has more to do with matroids and vector configurations and things like this. And I also was referring people to some lecture notes that I gave many years ago in a summer school in Vienna. And there's exercises at the end of there. You can take the 4 from there. You can take it from the list that's on the PDF in the syllabus, but 4 questions from the second half too. Or you could just give a 20-minute talk anytime during the semester, but you have to talk to me about what paper you're going to talk on. I've got some possible papers suggested on the syllabus. You could convince me that another paper is relevant. We'll be flexible about it. Okay, another thing about U of M grad students. Some of you should be skipping this class on certain days, okay? You were very, what's the word, cagey when you filled out my when to meet schedule, some of you Minnesota students. You did not point out that this 12:20 time actually does have a conflict occasionally, because Dick McGehee, our director of graduate studies, sometimes has sort of what I would call professional development type talks and meetings, community building meetings, how to deal with the pandemic. These sorts of things will come up occasionally on Mondays and Wednesdays in the department, and be on the lookout for those. Please skip this class, go to those things. Those things are important, okay? We want you to be happy. We want you to build community and learn how to be a mathematician. So get your priorities right. This class is not as important. And there's videos that are recorded anyway. Okay, office hours to be determined. I suspect I'll do a when to meet thing for the office hours, but let's not worry about it now when the office hours are going to be. There should be a total of 3 hours because it's 3 hours of lecture. And would anybody like to organize a study group? Would anybody like to set up a Discord channel? Yeah, that would be nice. Some of you are very good at this. And when I taught my course last semester, for a 4,000, a sort of upper level undergrad class, as I was saying, could somebody set up a Discord channel? Somebody set up a Discord channel. So feel free and just let me know. I'll put the link, and then I think that's a great way to organize study groups and put references when people find cool other lectures or sources about this same material. Oh, there's already a Discord channel in the UM grad server. Gail, would you give us the link in the chat? Great. Excellent. Yeah, and email it to me later, Gail, just in case I missed downloading the chat. Thank you very, very much. Okay, so yeah, study groups would be wonderful. So having said all of those things, any questions before we just start moving on to what the course is really about? No, we're okay. Yeah, you can use the chat, unmute yourself, that doesn't matter. I'm inching up the screen. Okay. All right, so what's the plan? This is a course about combinatorial rings and the Kähler package. What the heck is the Kähler package? I don't know. We'll find out later, but don't worry about it. We will eventually figure it out. And I'm going to try to give you some overview of what are the questions that are addressed by these combinatorial rings? What kind of questions are we going to be looking at? And how might some rings in some way become relevant? It actually takes a little while to get to see where there might be some rings that are relevant. So today, and I think Friday and probably Monday, I'm going to be just giving you an overview of who are some of these rings, who are these questions, who are some of the rings, and why might they be relevant. Okay, I have to be a little bit patient to even get to through the overview. So let's start. So this is combinatorics. We're going to be dealing with, we're going to be dealing with a different pen color, finite sets. And these are going to be geometric sets, and they're going to be things like points in Rn, maybe in Rd, points, actually, let's say vectors in space. And when I say space, we're going to start out with Euclidean space, d-dimensional Euclidean space, or maybe we're going to start pretty soon with the vectors. They're going to be in k to the d, where k is a field. Might not be the reals always, but we'll try to draw a lot of pictures over the reals. And what they do is these finite sets of points, they give us discrete geometric kinds of sets that have cardinalities or dimensions or ranks or whatever that we're going to try and count. So I'm going to say we're going to get discrete geometric sets of points out of them, or sets, excuse me, that we might count according to their cardinality or their rank or their dimension or something. I'll be getting to examples in a moment. And that's going to give us a sequence of numbers when we count how many have cardinality 1, cardinality 2, or dimension 1, dimension 2. We're going to look at these sequences of numbers and say, what can we say about these sequences of numbers? So that's the general question. What can we say about these sequences of numbers that come out of it from these discrete geometric settings? And the fact is, people ask different questions in the different contexts, and we've got different levels of understanding, different levels of completeness for our answers. Okay, so I don't know, let's flip the page here. Let's go to the next page. Any questions before I go further? Example, and this is the one that will occupy really about half the course. Points. I'm really thinking P1, P2 up through Pn in R to the D, so d-dimensional Euclidean space. They give rise to, I'm going to draw these squiggly arrows, meaning give rise to or have associated to them convex polytopes, a convex polytope. I'm going to tell you what that is. Convex polytope, capital P. P is going to be defined to be, okay, so this is a notation that I use a lot, is I'll use colon equals to mean I'm giving you the definition of the object on the left of the colon equals. The convex hull of, conv of, and then I'm going to write this set P1 through Pn. I goes from 1 to n. Okay, so what the heck is this conv thing? I'm saying the convex hull of the set of points. Convex hull of. And what is this? This is the smallest convex set that contains those points. There's many ways of saying this. Smallest convex set containing them. It's all the convex combinations of them. Let me write it that way. So it's the set of all things that you could get by taking Ci, Pi, I goes from 1 to n, where the CIs are non-negative reals and their sum is 1. That's what's called the convex combinations of those points. And let's draw some pictures. Like if we were in a one-dimensional space, if I'm on the line, if I plunk down a P1 and maybe a P2 and maybe a P3 and then maybe a P4, then their convex hull is going to be, this line segment. And that's my polytope P. And the points that weren't at the ends, the end points, actually turned out to be irrelevant when we were producing the convex hull. What mattered here were the leftmost and the rightmost actually determined the convex hull, okay? And for D equals 2, right, convex polytope ends up being a polygon. Maybe this is P1 and P2 and I don't know, P3 is down here and P4 and we got a P5 and who knows, maybe there's a P6 in here and maybe there's a P7 that's on the line segment between P2 and P5. And then when I take their convex hull, oops, let's do it in this color. I'm gonna get this polygon and that's my P, okay? And yeah, let's draw some pictures for D equals 3, which is perhaps the place in which you first think about polyhedra or polytopes that are more fun. For D equals 3, we've got these things like, ooh, did I go too far here? Oh, I went way too far, sorry. Let's do D equals 3 here. I might have something that looks like a tetrahedron. If I took 4 points in 3-dimensional space, P1, P2, P3, P4, and I'm going to stop putting in, like points in the interior, points on the edges, because as we can see, they don't really affect the convex polytope that comes out of this. And some other examples that I'm sure you're familiar with are cubes, right? Or maybe you're less familiar with, but I'm sure you've seen, some of you, the octahedra. Oops, got an extra point in there. I told you I wasn't going to put an interior point in there, I did. Okay. Anyway, and so what question are we going to ask here? How are we going to get a sequence of numbers in these examples is by looking at the number of faces of these convex polytopes in each dimension. And so the sequence of numbers that I'll get is, let's define it as f underbar of P. This is the F vector of P. And what's defined to be is a sequence of numbers. I'm going to call it F-1, F0, F1, F2, F3, Fd-1, Fd, where Fd is just asking how many faces of the polytope are there of dimension I. Number of I-dimensional faces of P. And now we already get into some definitional issues with saying, what the heck is a face? What is the dimension of a face? What's with F-1? So let's deal with these. We will be very precise about these later, but let me just kind of quickly go through some of the definitions to make clear what I mean. So first of all, you probably know what the dimension of a face is. And 0-dimensional faces, these are vertices. So these are the things at the corners, right? We're counting up those things. And 1-dimensional faces should be edges. So these are these things. Okay, we want to count up how many of those there are. And then there's two-dimensional faces, which would be polygonal faces, you know, like the squares on the front of the cube would be contributing to F2. So let's deal with this strange thing. This thing's always going to be a 1, and this is for the empty face. So you might think that's a weird thing for me to do, but we'll see later. You do want to count the empty face in the F vector. It makes a lot of sense. It makes the calculations work better. And it is a negative one-dimensional face. Take it as convention, okay? If our polytope is in d dimensions and if it's full dimensional, then it itself is the only d-dimensional face. The FD will be a 1, and that's, sorry, let me not. Oh, okay, yeah, so it's P itself. If P is full dimensional. And when I say full dimensional, I mean d-dimensional if the points were in RD, right? It could be that I stuck only like, I don't know, 3 points in a 3-dimensional space. They're only going to make a triangle at most. That would only be 2-dimensional, but let me assume that I've got enough points to actually make something 3-dimensional, excuse me, d-dimensional in my d-dimensional space, okay, when I take the convex hull. All right, what's a face? Now, maybe you think you know what a face is already, but a face, let's just to be clear, and this is going to be the way we're going to need to think about it later. This is actually going to be a very functional definition for us. A face of P is the intersection of our polytope with the hyperplane that defines some half space which contains P. Okay, so is H intersect P, I'm going to write it down, where H plus is a half space containing P. And H is the hyperplane in the half space. Okay, let me draw you a picture. Let's go back up here. Here is a hyperplane H. A hyperplane is a codimension 1 affine linear subspace. It's not a subspace that goes through the origin, but it's a translate of a subspace that goes through the origin. I didn't even draw where the origin was in this picture, okay? And on this side of H is H plus. H plus is everything over here that I've shaded in green. I didn't shade all of it, but it's all this stuff over here. And notice this half space that has this hyperplane as its edge, it's, you know, defining it as its boundary. This half space over here contains my polytope P, but then when I intersect just the hyperplane part of the half space, I get this face F that I'm about to darken. In this case, that face, oh, I didn't call my typical face F. Let's call it typical face F. Okay. So back up here, that was an F. And let me draw you another one, just to same sort of looking polytope P. Here's another F. If I took a hyperplane that just sliced through that vertex, that's another H. Maybe I'm going to take, well, I'm definitely going to take this half space, what's over here on this side of the hyperplane. That's my half space H plus. So that one contains P inside the H plus, but when I intersect with the H, I just get this face F, which is a vertex, which is a 0-dimensional face. Okay? So I'm just trying to be precise. What do I mean by faces? And I hope you know what I mean by dimension of a face, but I'll say it, but I won't write it down here. We'll come back to it later. The dimension of a face, F, is take that face and take the smallest affine subspace that contains it. Now that affine subspace is a translate of a linear subspace, which has a dimension, right? We know that linear spaces have dimensions, right? Therefore, affine spaces have dimensions, and therefore faces have dimensions, because you take the smallest affine subspace that contains them, and that's its dimension. Okay, I said a lot of words. I didn't write much down, but we'll be more precise later. Any questions?
Does this mean that the definition of a polytope is that it's an intersection of half spaces?
So that's a great question, Peter, because if I said a polytope was an intersection of half spaces, I would have to add the condition that it's bounded, that it's compact, right? I could have what you just defined as what people usually call a polyhedron. So this is, for example, if I take a bunch of half spaces defined by these sides of these hyperplanes in R2, this thing would be an unbounded polyhedron. Maybe I should make it pink again, but anyway, the point is, it's this. This is an unbounded polyhedron because it's not compact. And that's an intersection of half spaces, finitely many half spaces. But bounded polyhedra, it's a theorem that if you've got a polyhedron and if it's bounded, then it's the convex hull of the set of its vertices, the extreme points. So yeah, there's a minor subtlety there. Yeah, Sam, did I answer the question, do you think? I think I answered the question, right? Yeah, okay. Good. So yeah, please keep asking questions. Questions are important to the class.
So is the F-1 face, is that useful for essentially the same reason that reduced homology is useful in comparison to normal? Cool.
Absolutely, for exactly the same reason we need to include it. Yes. Great question. Yep. Okay, so just to write down some of these numbers right here, the F vector is kind of boring. It's got an F-1 and an F0, and they're a 1 and a 2, right? Two vertices and two vertices and a negative one-dimensional face. Ooh, I forgot to put in the F1. You're going to realize that there are a lot of times in which I want to omit the FD, but not yet. F1 is 1. And for this polytope here, we've got the wrong color. F of P is, what is it going to be? A 1, a 5, a 5, and a 1. And that's F-1, F0, F1, and F2. Okay. And for these, let's do it. Maybe I'll stop writing the F of P and just write F. What do we got here? 1, 4, 6, 4, 1. Those are binomial coefficients. You probably recognize those. That's because this thing is a simplex. It's got a very, very simple structure. But just to get our convention right, F0, F1, F2, and F3. And for these two, let's compare them because this is going to be important. What do we got? A 1. I've got 8 vertices. I've got 6 faces. Try again. 8 vertices. How many edges? 12 edges. 6 faces, and then the polytope itself. Whereas for this octahedron, it's, let's see, there are 6 vertices, again 12 edges, 8 faces because it's an octahedron, 8 for octa, no, octa for 8. And that's the F vector. And a reasonably important point that's going to come up is, was it a coincidence that these numbers and these numbers are reverses of each other? No, actually, the relationship between these two polytopes, so they are polar dual. So this is P, this is, I'm going to use the Gunther-Ziegler notation, P with a triangle for the polar dual. So there's some kind of an involutive operation on polytopes. It sends one polytope to another, and it sends the F vector of one of them to the reverse F vector. You read it backwards. So I-dimensional faces in one correspond to D minus 1 minus I-dimensional faces in the other. And it is an involutive operation. So this is actually P dual dual, P itself. But I'm not going to tell you yet how you do the construction. It's not a hard construction. It's something that we'll talk about, and I'll be referring you to Gunther-Ziegler's lectures on polytopes for a lot of the details about it. But we're going to use this construction all the time. And we're going to freely pass between polytopes thought of, for example, as the convex hull of a set of vertices, points, versus thinking of them as an intersection of half spaces, like Peter asked, right? A polyhedron. So one of the relationships between them is you can think of this polytope as being an intersection of half spaces that correspond to the vertices in the original. Okay, so the vertices here correspond to the maximal dimensional, the facet half spaces there. We'll come back to this, but I just want to say that there is some kind of a duality going on that explains this. Okay.
Professor, I have a question.
Yeah.
So I noticed for the tetrahedron on the left, that I know that it's also called all the simplex, and then also that at the F vector for that simplex is actually pretty nice because it's a row of Pascal's triangle.
Yep.
So that makes me wonder: is it possible to construct the F vectors of other more complex polytopes, like the I don't know what's that called, the like rhombus in the bottom right, by thinking about like the simplices that build it up?
Oh, yeah, absolutely. So in fact, as you pointed out, right, this is a row of Pascal's triangle, and so the F vector here, right, this is really this is what is it? 3? No, not 3. Let's try again. 4 choose 0, 4 choose 1, 4 choose 2, and so on. And I invite you, well, I didn't define what's the hyperoctahedron, right? What's the higher dimensional analog of this? And I didn't define what's the hypercube, but they're not too hard to define. I could define them. And then there will be simple formulas for these numbers that involve binomial coefficients and powers of 2. And if you keep me talking like this for too long, I'll make this an exercise. No, but it's actually an easy exercise to come up with these once we define what the hyperoctahedron is and what the hypercube is, to write down formulas like that in general. Yeah, it's a great question. Okay, how are we doing? Other questions? Sneaking up here. Oh, did I take away the d equals 3? Yes, I did. Good. So let me tell you about historically kind of one of the first questions. I mean, we could be going back to the Greeks, and we know that there are definitely some things one can say about F vectors of polytopes, right? They knew things. No, Greeks, maybe to Euler. Let's go to Euler. You know, there's Euler's formula. I'm sure some of you know there's relationships between the number of, the F0 and the F1 and the F2, you know, these things, V minus E plus F equals 2. Yeah, we'll come back to that, okay? But one of the questions that's gonna motivate where we're headed came up in the 1950s here about polytopes. So this is, I'm gonna say 1950s, roughly speaking. The question of how large can Fi of P, the number of I-dimensional faces, be if we fix the number of vertices? the f0 of p, let's just call it n. So I'd say I'm only got n vertices, like 100 vertices. How big can the number of, I don't know, 2-dimensional faces, 3-dimensional faces, in higher dimensions, you know, the 20-dimensional faces. We sort of lose intuition once the dimensions go up. And really, why is it the 1950s that this question came up? I mean, it could have been asked by the Greeks, by Euler, but this was motivated actually by the dual version, the polar dual version of this question. Let me explain why in the 50s people started to care about this. It's because that was when this thing called the simplex method for linear programming, you know, it's a certain combinatorial optimization algorithm, came into play and started being used. Simplex method in linear programming. So I'm going to remind you or tell you what the heck, this linear programming is a horrible name. It's really not very suggestive about what this thing is. So motivated by the simplex method in linear programming. Okay, as the polar dual question. So let me really ask the polar dual one. They weren't asking how many higher dimensional faces can you have if you fix the number of vertices. They were really asking how many vertices and edges, low dimensional faces, can you have when you fix the number of d-1 faces? How large can number of vertices, number of edges be if we fix the fd-1 of p to be n? Okay, so fd-1, that's this number of top dimensional boundary faces, the number of, yes, the number of those. Okay, so let me draw you the picture that happens in linear programming. In linear programming, what you're looking at in some high dimensional space is you got some variables, you know, like x1 and x2. And I don't know, when I teach the hokey version of linear programming, I'm saying x1 is how many acres of beans I'm going to plant and how many acres of corn is x2, you know. I'm a farmer and I'm a linear programmer. And there's constraints like, you know, it's going to be non-negative. The fact that, okay, so the number of beans is going to be non-negative. The number of acres of corn is going to be non-negative. And then there's other constraints, like I've only got so much money to buy the beans and the corn, and so there's a cost, and that constrains me to buy a certain amount. And then there's only so much field space that I have, and that presents another constraint on how much I can plant. And there's only so much water I can use to irrigate, you know. And so basically you get this feasible region. And you know me, I'm all about maximizing profit. Okay, so there's some functional called profit f that's linear. It increases in some direction. And what I'm trying to do is I'm trying to figure out what's the point in this, you know, beans and corn space where I'm going to maximize the value of f. And the theory of linear programming and convexity shows us that, well, it's definitely going to happen at some vertex here. You know, we got the different vertices. Maybe I'll start out thinking, I will plant 0 beans and 0 corn fields, you know. But then I realized, I think it'd be better if I actually move along this edge and switch over to maybe that vertex where I'm actually planting some beans. And then maybe I could do better if I go up here to that vertex along that edge. And so linear programming, you know, kind of travels. It gives you an algorithm that travels along the vertices, increasing the value of the functional as you go along the edges in some systematic way. And they were worried about how many steps the algorithm would take. And so the idea is there's n constraints, n facets, n of these d-1 dimensional faces. I'm going to call them facets. So I haven't defined it yet, but now I'm defining it. d-1 dimensional faces are facets. So these n inequalities, and what they were worried about is how many of these little orange vertices are they going to have to travel through? A crude upper bound on the number of steps in the linear programming, you know, algorithm by simplex method, a crude upper bound is just f0 of p. How many vertices are there? Or you could get another crude upper bound by saying, well, you're traveling along edges. as long as the functional keeps increasing, you're visiting different edges, you know, the number of edges is also an upper bound and the number of steps. And so you can see why they would care about this question suddenly in the 1950s when they had developed linear programming. Does everyone understand the motivation for this version of the question? Okay. So there was somebody who cared about this question and actually made a conjecture. So we are going to prove this conjecture relatively early on. This will happen pretty soon once we start developing the theory. We will prove using a certain ring, in fact, which isn't the first way it was done. This conjecture of Motzkin, it's called the upper bound conjecture. And this was so it's Motzkin's upper bound conjecture. Sometimes people even abbreviate it UBC. From 1957. But as a theorem, it's Peter McMullen. Theorem of McMullen. I should emphasize this is Peter McMullen in London, not Kurt McMullen, who I think is at Harvard. I can't remember. Okay, so what did Motzkin conjecture? He said that he could tell you if you're in D dimensions and if you've got n vertices. I'm switching back to the original formulation where I fix the number of vertices and I ask about the number of I-dimensional faces, how to make it as big as possible. He conjectured a polytope that'll do it. In fact, simultaneously for all the I-dimensional faces. Any D-dimensional cyclic polytope, I'm going to tell you what that is. D-dimensional cyclic polytope with n vertices, C and D, I'm about to define it. Okay, I'm going to define it in a second, but let me put the end of the sentence. Simultaneously maximizes Fi of P among all D-dimensional polytopes with n vertices. So here's the end of the sentence. D-dimensional, I'm going to start writing D-dimmel because dimensional is such a long word. D-dimensional polytopes with n vertices. Okay. And so what's a cyclic polytope? Yeah. It's the convex hull of these endpoints, x of t1, x of t2, up through x of tn. Okay, so I didn't tell you who x of t is. I didn't even tell you what t1 and tn are. So these are going to be real numbers. You just pick n distinct real numbers, and x of t is this vector that's t squared, t cubed, t to the fourth, up to t to the d. So it's what's on people call the d-dimensional moment curve. It's kind of in algebraic geometry, it's this twisted, well, it's the twisted cubic if we're in d equals 3, but it's an embedding of p1 in p to the d minus 1. It's an interesting curve. So t squared, t cubed up through t to the d is what x of t is for a real number t. I think I better draw some of these for you. But before you say like, what the heck, let me draw some pictures of cyclic polytopes, okay?
Oh, can you scroll back up to that?
Yeah, question? Okay, gonna draw. CN2, these are easy. First of all, these t squared points, they lie on a parabola, right? We're in R2. Here's our parabola that's parametrized by t squared, right? These points. And now I just pick, I don't know, maybe this is t1, this is t2 on the real line. Maybe this is my t3, so I have to pick some real numbers, t4, t5, and then they give me these points on the parabola that are above them, and then I take the convex hull. So I get this line segment, this line segment, this line segment, this line segment, and that line segment. And no surprise, the two-dimensional cyclic polytope is a polygon, and it's got n vertices, and it's got a pretty easy F vector. So they're not so interesting for D equals 2, but let's draw D equals 3. Let me draw you C6, 3. Ooh, in my notes I wrote C6, 2, but I'm going to draw you C6, 3. So I am going to draw the same projection onto the x1, x2 plane, and we had our parabola, right, tt squared. But now what I want you to imagine is that there's a third coordinate that's at height t cubed out of the, I was about to say blackboard, out of my iPad. No, where my thumb is going, you know, out of your screen. And so if I pick like let me pick a T1 and a T2 and a T3 here on the real X1 axis, T5, T6. When I pick those and I pick these points, I can again draw the projection onto the X1, X2 plane as being in these spots. But now let me try to draw the three-dimensional picture. So the point is, this point is really high compared to this one, right? It's got its third coordinate is t cubed. It's way out of your screen. This one is less out of your screen. This one's less out of your screen than that. This one's into your screen a little bit. This one's even farther below, and this one's farthest below. So when I draw the convex hull, it's actually not that hard. It's going to look like this. First of all, I'm going to have the same kind of projected profile of a polygon, a sixgon there. And then I'm going to have edges that you can see in the upper part. Looks kind of like a scallop shell. And then there's these edges that you can't see in the lower part. That last one I drew kind of not dotted enough. I want that to be dotted like it's in the back. So there's sort of like a scallop shell in the back. In fact, I like to think of the three-dimensional cyclic polytopes as like a really confused scallop. Some kind of mutation happened and its top shell and its bottom shell didn't align correctly. They kind of. Does everybody get the picture of what these three-dimensional cyclic polytopes look like? Questions about the three-dimensional cyclic polytopes? Okay, so let's draw some F vectors. F of Cn2 is not too surprising, is going to be a 1, an n, and a 1, right? That's again F -1, F0, F1, and F2, right? They're always going to have the same number of vertices as edges because they're polygons. Here for for C6,3, the F vector is going to look like, what is it, 1, 6, right? All of those vertices are the 6 vertices that we started with. There's 12 edges, I think. You get 6 of them going around like that. And then there's 3 in the top clamshell, and then there's 3 in the bottom clamshell. So I think you get 12. And then for triangular faces, I have written in my notes 10. Let's see if we can get the 10 of them. Yeah, I think there's, whoa. Did I count that wrong? I may have counted that wrong. I wrote 10.
5 on the front, 5 on the back.
1, 2.
There's the one behind.
I'm really confused about.
Could we use Euler's formula?
We could use Euler's formula. That's a great idea. Yeah. Doesn't Euler's, I think I wrote the wrong thing in my notes. I think it's 8, isn't it? 1, 2, 3, 4 on the front and 4 on the back.
Did you do a different one for your notes?
No, I think I just can't count in my notes.
Okay, fair.
I think 10 is right because the one that goes T1, T5, T6, that's kind of in the back but on the top.
Hmm.
So there's 5 like coming out and 5 like behind the graph.
No, I think in the back I'm getting that one you just said, that one, and then a little skinny one there. I think it's 4 in the back. Yeah, 8. Everybody agrees with me. Good. Proof by intimidation. Okay. So here's the thing. So I said this theorem was due to McMullen, the proof of the Motzkin's upper bound conjecture. McMullen had many of the key ideas in this subject, not the rings part, but a lot of the other key ideas. And just to get to the rings at all, we need one of his beautiful ideas. And that is that the F vector is just too much information. Whoa, and sorry, I forgot to talk about a reduction. Let's talk about the reduction. It's not hard to see that when we're trying to maximize the number of I-dimensional faces, fixing the number of vertices, we may as well be talking about what are called simplicial polytopes. There's a construction that I'll show you that lets you pull vertices, and you'll have the same number of vertices, but more faces in every dimension, and get you to a simplicial polytope. So it's not hard to see using pulling vertices. That Fi of P is maximized for a fixed number of vertices by simplicial polytopes. Okay, so I will. What's a simplicial polytope? I have to define this. It means every boundary face is a simplex. And what's a simplex? It's when you have the minimum number of vertices to actually make a face of that dimension. So it's a d-dimensional polytope with d vertices. So for example, this prism, that's a polytope, but it's not simplicial because these faces are fine. Those are simplices. Triangles are simplices, but these quadrilateral faces, those are not simplices. This is not simplicial. But there's a way to pull vertices. So I'm going to pick a vertex here, V, and I'm going to pull V. And what it is you just, I'll be much more precise later, but you kind of move it slightly away from the polytope, and you always end up creating something whose faces look like a subdivision of the original. So it breaks faces. Where you used to have some collinearities, the collinearities get broken and increase the number of faces, and it gets you closer and closer to a simplicial polytope. So I'm gonna have to still, this one's not simplicial yet, but if I take this vertex V prime and pull that vertex V prime, then I think I will actually get to something which is simplicial. So let me, yeah, what I needed to do was get that back face to be subdivided into simplices. Oh, not just the back face, I also needed to get that one. No, the back one already was. It was, this one was the problem. That thing was a quadrilateral face, but when I pull the V prime, it gets broken. So there's a way to make this precise, but you can keep the number of vertices the same and weakly increase all of the number of I-dimensional faces. And so we know that there's always going to be a simplicial polytope that does the maximization. So what I'll talk about next time is how McMullen's ideas for simplicial polytopes, he greatly reduced the amount of information one needs to look at and just recast it in a more insightful way that is much closer to the rings. That's the point. He wasn't thinking about rings, but he was headed toward the rings when he recast the F vector in terms of the H vector. So I will stop there. I've already gone over a little bit. Any questions before I turn off the recording? And I'll hang out if there are more questions, but any questions that anybody wants on the recording?